So periodic properties. The first one we'll be discussing about is atomic radii or atomic size. So I want you to understand that what atomic size over here is. So for example, an atom is like this. We assume that there are some shells around. The inner part which I drew is the neutron. Okay. Yeah, an atom is like this. And then there are some electrons. Yes. So, for example, if this is the proton, I mean, if this is the nucleus, yeah, if this is the nucleus, then I'll take another color for this. Yes. Then this distance, as we see, is for what we usually call radii, and we assume all these distances to be equal in a Bose model. But that's what is ionic radii, the distance between the nucleus and then valence shell electrons. But then usually what happens is it's very difficult to do that. Yeah, it's more difficult to do this method. So the scientists do another easier method to find out the ionic radii. I mean, to find the radii, atomic radii. So, like for example, if two atoms are bonded covalently, then and let's just say this is their nuclei, and they have other shells too, but not considering right now. This distance, like the distance between their, yeah, the distance between the two nuclei are called atomic radius. This is called covalent radius. This is just a little bit out of syllabus, but I'm just telling to make it a little bit more easier while understanding it. And then for ionic ionic bonds is basically like they're close after losing the electrons, they are together. So they just calculate the distance between the two. Okay, what a circle. Okay, anyway. Then again over here, they just calculate the distance and then we use it as atomic radii. But yes, that's atomic radii. So let's discuss. Yeah, that is atomic radii, and I also want to tell this general rule which we are going to discuss. We'll use it for other periodic properties also. So yes, as I was saying, the general rule which we're going to discuss right now, I'll draw a diagram to explain it. So suppose this is an atom. Suppose this is the atom, and there's electrons on it. And then there's a nucleus, very small nucleus. Rutherford's experiment showed that the nucleus is very small. So the distance between for example, if this is the distance between the valence electron, you take it as r, and then we'll take it as r. Valence electron and nucleus. The force on the electrons by the nucleus will be given, like for example, We learned gravitational forces. F is equals to G1 and Gm1 m2 whole by r square. Whole this this is for gravitational force. For electric force or for electrostatic forces, it's K. So this is the like gravitational constant. This is constant dielect. This is a constant for dielectric constant for the electric forces. Yes, Q1, Q2. So the charge is the charge of the nucleus is Q1 and the charge of the electron is Q2 whole by r square. So this is just a revision of last year's physics concepts, but we'll be using it here. So as the distance between the electron and the nucleus increases, it will increase by the square of it, right? The force will decrease by a square of 1 by force is proportional to 1 by square. And then as the charge increases, the force increases. So if you want to have the maximum force on electrons, then you should have the closest possible and maximum possible nuclear charge. So that is, you can also learn it without this formula, but I'm using this formula for a future purpose. So now we'll be discussing about the trends of atomic radii. As I've now explained what atomic radii is. Trends of atomic radii now. So I'll get the periodic table, a small one here. Yes. So as we go across a group, as we go across a group, across a period, I mean, the we know that the number of the valence shell remains the same, so this distance remains the same, but the nucleus gets more protons in it. Lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6. So since this increases, although that you can argue that there are some electronic repulsion, the nuclear charge increment because of the new electron which comes, the electrons repel each other, but the nuclear charge increment overcomes it, and then the size of an atom reduces. So by this theory, you would assume that noble gases will have the smallest size in a period, but that is not the truth. That is not the that is not what we know. The smallest element in a period is the halogens or 17th group element of that period. Why is this? Why is it not noble gases? Could be a very good question. That's because, as we have discussed before, it's more easier to calculate ionic radii and covalent radii. So, for all of these elements, they form some bonds, some molecular bonds, and you can easily determine the covalent or ionic radii. But for noble gases, they do not form any bonds. They're already stable. They have valence electrons complete, so they don't need to form bonds. So for noble gases, what they do is they just find the closest possible distance, and this does not needs to be their radii, right? This it's just a try to find the closest possible distance, and it's not very accurate, I would say. And also, there's another reason, which is because when you get more and more electrons as the outer shell, the electronic repulsion also will play a part, like it will play a bigger part, and so probably that also a little bit balances out the nuclear charge increase. So that is two possible reasons. So yes, then so as we go across a period, it increases. And then down a group, we know the R will increase. Like hydrogen will have only one shell, lithium will have two shells, and then as you increase the number of shells, the distance between the valence electrons and the nucleus will increase. And you can say that, okay, but when we're going down, won't the nuclear charge also increase? Yes, nuclear charge does increase. There's no denial of that. But as we just saw, it's KQ1, Q2 by R square. No, R square proportionality. So it's 1 by R square. So the distance factor overcomes the increase of nuclear charge, and therefore the force on these electrons decreases and they become bigger because the nucleus cannot hold them more closely. Yes. So then that is why it decreases, and decreases down a group. Yes. So potassium size. Sorry, I made a mistake here. Across a period, it decreases, and down a group, it increases. So by this, we know that we can say that iodine's atomic radius is more than the fluorine, and fluorine's atomic radius is lesser than of lithium or boron or any of the elements over here. That is atomic radii. Now, now we'll be looking into the next property, metallic character. So again, as we discussed over there, again as we discussed in atomic radii, metallic character is just the ability for an atom to lose electrons at the easy with ease. Yes, with ease. So atoms which have lesser number of electrons will generally tend to lose electrons more easily. Like since they are just one since after they lose the electrons, they can form their noble gas configuration. So atoms like lithium, beryllium, or any of the first three groups, they will lose electrons comparatively more easier as they can form noble gas configuration. Remember, one rule in chemistry is all reactions and everything which happens is to get stability, and noble gas configuration is the most stable state. So lithium, beryllium, boron, sodium, magnesium, aluminium can easily lose electrons and form noble gas configuration. So then the lithium will be, for example, lithium has just one electron. So after it loses it, it will become noble gas configuration. So beryllium has two electrons, and we already learned in the previous while talking about atomic radii that across the group the nuclear charge increases, but the valence shell remains the same. So force exerted by an atom, the Q1, Q2, Q1, Q2, in that the nuclear charge Q1 will increase, but the radius will remain almost the same. So by this reason, beryllium clings on to its valence electrons more strongly than lithium does. So lithium loses its valence electrons more easily than beryllium does. And this is the general trend across a period. So across the period, since lithium since the group 1 electrons clings to the electron, group 1 elements clings to its electrons with less force, it can lose it easily also. So they have metallic characters, this ability to lose electrons, to lose E minus and form cation. Yes. So across the metallic character decreases. That's also a little bit common sense. Also, you can see here we have all the non-metals and we have the metals on the left side. And then down a group, we know that down a group the electrons, I mean, the force on each electrons, although the nuclear charge increases, we've discussed that the force is proportional to 1 by r square. So r square overcomes the q increase, and there's a net decrease of force on the electrons. So if there's decrease of force on electrons, then we'll know that it becomes easier to lose electrons. So down a group, the metallic character increases. Yes. Yeah. Now we'll be discussing about non-metallic character. So non-metallic character decreases down a, I'll just get one more period. So yeah, non-metallic characters, the ability to gain electrons easily. And non-metallic character also depends, yes, it depends as on the two factors we spoke about, atomic radius and nuclear charge. That's what basically determines everything. So in a Bohr's model, as we go towards, across a group, across a period, as we go from group 1 to group 18, we know that the charge increases. And we have already discussed. So by now you'll be knowing that across a period, the electrons are held with more force. So if a new electron comes, it's becoming more easier to accommodate because already they're held by more force. But when you're in the, let's say, group 1 of period 2, like when you go towards the left, not towards the right, already the atoms are although the nucleus holds the valence electrons with lesser force, so it will be difficult to add more electrons. Whereas if you go towards the left, towards the right of towards across a period, the nucleus holds an atom with with more force, so a new electron can be easily accepted. So across a period, the non-metallic character increases. And down a group, as we go down a group, we know that the ability to cling on to the electrons, the valence electrons of the nucleus, it decreases. So it decreases. So then when the ability to cling on to the electrons decreases, then how can you add more electrons? Already the existing electrons are it's holding with less charge, less force. If you add more electrons, how can it hold more electrons when already the existing ones have less force? So that is why it decreases. Like the electronic repulsion will overcome it, and non-metallic character decreases. Yes. Now we'll be looking at chemical reactivity. So as we have learned, chemical stability is basically noble gases. When you have noble gas configuration, you have the lowest energy, and you wouldn't really want to exchange it for a higher state of energy. So across a period we go, the chemical reactivity of elements, as we go towards the middle of the periodic table, the chemical chemical reactivity increases, but from middle of the periodic table, it uh, yeah, it gradually from the beginning it gradually decreases. Then in the middle of the periodic table, it's the least, and as we go towards the right, it increases. It's because uh, as the number of electrons increases, um, you need more energy to remove all of its electrons in order to form bonds. And as you go, so the chemical, so ionic bonds are formed in the in the center of the periodic table. I mean, in the mid, as from the left side, right end, and the left end and the right end, you can see ionic bonds. As you go towards more centrally, you have more covalent bonds. So that's chemical reactivity. Ionization energy. Ionization energy or electron ionization enthalpy is the it's the energy required to remove one electron from the valence shell. It's the energy required to remove the valence shell electrons. So when we go down a period, we know that we have discussed earlier that the when we go down a period, we have discussed that the number of shell increases. Sorry, down a group, we have discussed the number of shells increases, and then the charge, the effective charge on each valence electron also decreases because the distance r square overcomes the increase in nuclear charge. We have discussed it. So as we go down a group, there is a net decrease of nuclear force. So we just need to give lesser energy in order to overcome the nuclear force on the valence electrons. So down a group, the ionization energy decreases as the nuclear charge on each valence electron decreases. So remember, as the force decreases, you just need to put lesser energy get it. As at nuclear force on the valence electrons, they as the nuclear force becomes bigger and bigger, you need to give more and more energy to remove the electrons from the atom. And across the period, we know that the nuclear charge increases. Therefore, the shell number remains the same. So R effectively remains almost the same, and then the Q factor increases. So that's net increase in the so there's an increase in the force by which it holds. There's an increase of force by which it holds the valence electrons. Therefore, across a period, the ionization energy increases because it takes more energy to overcome a bigger force. That is just general knowledge. So now we can ask, so then now we have the people usually say cesium is the most, cesium has the least ionization energy, which is true, and helium has the highest ionization energy. And one more thing I want to say is that you can ask why francium is not the highest ionization energy. That's because francium is francium. Usually you will say that's a radioactive element and it's probably not determined. But I went and checked Google, and actually it says that francium's ionization energy is more than the of cesium. I don't want to explain the reason now, but I just want to say by this we know that in chemistry there are so many exceptions. Not everything generally we learn are not general properties. For example, when we go towards the right, we say that the ionization energy in, increases, but for two elements it does not. Like for example, in magnesium's ionization energy is a little bit more than aluminium's ionization energy, and nitrogen's ionization energy is more than of oxygen. So there are a lot of exceptions, but in our syllabus, we don't have to learn the exceptions. Yeah, electron affinity or electron gain enthalpy is the ability of electrons to gain ability of atoms to gain is the energy given by the atom when it gains an electron. So let's say won't it take energy to gain an electron, but no, when it gains an electron, it goes one step closer to noble gas configuration. So it loses energy. It loses energy as it gains electrons. So the energy gain, yes. So as the number of electrons, as the nuclear force on each atom increases, it gives like more. It gives as the nuclear charge, as the force exerted on each atom increases, more energy is given. So when you're going from left to right in a periodic, in the period, um, you see an increasing trend of electron affinity, and when you go down a group, that's the force on each electron decreases. So electron affinity also decreases as as a as another electron is gained. It's gained into a bigger shell, like it's gained into a shell which is more further away, and therefore uh, the energy value of that shell is less, so it decreases. For example, lithium, we know that when an atom, when an electron is close to the nucleus, it must be having a lot of energy. So when it gains, so when lithium gains an electron, it's close to the atom, so it gives a lot of energy. But then when cesium gains an electron, it's very further away, so this shell has very low energy value, as this distance is more than this distance. So that's why down a group it decreases, and across a period also you can make this. You can give a similar explanation to it. And oh yeah, and I have to tell the most electronegative element is chlorine. Electron affinity is chlorine, has the highest electron affinity. You can say why does not oxygen? Okay, if chlorine has it, then why not fluorine has it? Like why? Okay, fine. You can say that technically it should be fluorine according to your theory, but then according to the theory given by you, so doesn't mean that I gave the theory, but the theory was devised by someone else. But I just explained it. Theory explained by you. So you can say that chlorine has higher electron affinity than fluorine because chlorine. It's because fluorine has. It's a very small atom, so there's so many electrons around it. So when you add when you add like one extra electron, so the 8 electron, the other electrons repulsion overcomes the nuclear attraction. So basically, you would need more energy in order to put it. Like the electrons keep. It's like you can think someone is. You want to enter a room, but then someone is pushing you, so you need to put more force to go inside it. Whereas in chlorine, since it's a little bit bigger, the spacing between the electrons is also more, and therefore the electronic repulsion decreases. Okay, so it's chlorine that we know, and then the least electron affinity must be cesium according. Next, So you can remember electron affinity and ionization energy increases across the period and um, decreases down a group. It's same for both of them. So electronegativity in a bonded pair. In a bonded pair, electronegativity is the we know that in a bonded pair that the electrons are not, they're not spaced in the middle of the both bonded pairs unless it's a non-polar covalent compound. But um, so electronegativity is the ability of the nucleus to pull the bonded pair of electrons. So remember, it's bonded. In electron affinity, which discussed, it was not bonded pair. Uh, it was just a, it was just basically the energy given out. Electronegativity is not the energy given out, it's just a tendency. It's a tendency to attract the bonded pair towards itself. So electron affinity depends on basically two things. One is, as we know, one is the nuclear charge. As nuclear charge increases, to pull the electrons towards itself, the tendency also increases. So basically, which means that across a period, since the nuclear charge increases and valence shell remains the same, across a period, the electron affinity increases. And down a group, the electron affinity, since we know that the size increases and nuclear charge, so the effective force on the the effective force on the bonded electrons decreases, and therefore electron affinity decreases. So yes, I think that's about it. And the one more thing, the most electron negativity is not chlorine, but it's fluorine. Sorry, fluorine is F, not Fl. And this is the highest electronegativity, and lowest electronegativity is cesium. So I hope it explained well, and this time I tried to do it better than the last class, and I will improve over the classes. And if there's any mistakes you spot, please do tell us. And thank you. Have a good day, bro. And thank you, and have a good day. Please also recommend suggestions if you think we can improve any of our anything about the class. Thank you. Bye.